Welcome to the pre-calculus notes for Essential Skill B4 and Essential Skill B5. We're just going to do a little bit of wrap-up on Skill B4, graphing rational functions, introducing a shortcut, and then we're going to look at limits. First, we look at a pattern for when functions might have a y equals 0 asymptote. Now, this is a horizontal asymptote, which is a type of end behavior. So that means we're doing long division to find this. That means we need to expand all of these factored form polynomials. Now we can divide. As you can see, there's nothing that's going to make x squared go into 2x because the degree of x squared is too high. So we're already done. This has 0 plus remainder. By our rule, the quotient is 0. And so that means our end behavior asymptote is y equals 0. This one's a winner. Similarly, if we try to do long division with x squared plus 7 going into 1, we don't have anything for the quotient. X squared won't go into 1. And so this is all remainder. So that means our end behavior asymptote is y equals 0. So that is another one. To test this last example, I'm just going to look at the first term. That's going to be enough to tell us what the whether the asymptote is going to be 0 or not. The quantity 2x squared is 4x squared times another x is going to give us a lead term of 4x cubed. The denominator is going to start with x squared. That means the first term of our quotient is going to be 4x. That's going to match 4x cubed. So this is not 0. You've probably noticed by now that when the numerator has a degree that's too low to support a quotient, we're going to get y equals 0 as our end behavior asymptote. This is the main focus of our shortcuts. We're going to look at the numerator's degree as compared to the denominator's degree. Let's see what happens when the two have the same degree. Again, horizontal asymptote is a form of end behavior, so we're looking at long division. Our question when we do long division is what turns 3x into 2x? Well, we're going to have to multiply by 2/3. 2/3 times 3x is just 2x. We flip the signs and add. There's our horizontal asymptote. Let's look at what happens in the second example. Have you spotted the pattern yet? Here's a hint. The ratio of the lead coefficients in the first example is 2 to 3. 2/3, y equals 2/3. 4 over 2 is 2. This suggests that the lead coefficient ratio is going to be the horizontal asymptote in this case. We can verify that by doing it with variables. Now what we need to do is look at what turns bx into ax. Well, we want the b to be canceled out, so we're going to put that in the denominator. We want to be left with an a, effectively a numerator. So we look at a over b. A over b times b over x cancels the b, leaves the a. There's our ax. The rest is constants. It's just going to be remainder. As we suspected, the horizontal asymptote is the ratio of the lead coefficients, a to b, a over b. We can say this formally by looking at a generalized polynomial. In this case, we have the same degree, and so it will have a horizontal asymptote of y equals a over b. Our third case is when the numerator's degree is greater than that of the denominator. In that case, we get what's called a slant asymptote. Those were the asymptotes that looked linear, that were not horizontal lines. If the degree is higher like this, there is no shortcut. We have to divide. Take a moment to try this example, just to make sure that you know what you're doing with this. Here's my solution. I'll mark the step numbers to correspond with this how-to. Now we can look at limits. First, we review the end behavior limits that we've already looked at. When we're just dealing with a polynomial, not a rational function, we just look at the number line analysis and look at the leftmost sign for the left limit and the rightmost sign for the right limit. Try a number line analysis on example 1. Be sure to use the shortcut. Here's my solution. So our answer for the left end behavior limit is negative infinity. For the right hand limit, positive infinity. When we look at a graph, looking at the right hand limit, we're saying what happens as x increases? What is y doing eventually? So after all this mess, it's going to settle in and go up and increase without bound. Similarly, for the left-hand limit, the final step for the y values is to go down, down, down to negative infinity. In the case where we have a horizontal asymptote as an end behavior, we know that the graph is going to stabilize near y equals k, some number. If a graph has a horizontal asymptote, that simply becomes the right hand and the left hand limit. We now have shortcuts for finding horizontal asymptotes. If numerator and denominator have the same degree, then the end behavior asymptote is simply the ratio of the lead coefficients. Therefore, in the long run, as x approaches infinity, the limit is going to settle in on that end behavior asymptote. That's your answer. It doesn't matter how high the degree is. If they're the same, then the horizontal asymptote is the ratio of lead coefficients. Recall that when the degree of the numerator is small, the horizontal asymptote is just y equals 0. This becomes the limit. Visually, when we mark a horizontal asymptote, we are implying that in the long run, the y values are going to converge on that y value. So both left and right side limits will be converging on that horizontal asymptote of y equals 1. When we have a vertical asymptote, our answer might be different depending on whether we approach the asymptote from the left or from the right. We'll use the same notation that we used with piecewise functions to refer to the left or the right side of the asymptote. The general limit is going to follow the same rules that it did with piecewise functions. If both sides have the same limit, then the general limit will match. If the side limits are different, it does not exist. Take a moment and try these examples. See if you get it right. When x approaches -1 from the right, we are still approaching -1. We find the function line and we're heading toward -1. Y is increasing without bound. When x approaches -1 from the left, we're still approaching x equals -1, and y is increasing as we do so. The left and the right side limits match, and so our general limit is the same. When x approaches 3 from the right, y is increasing without bound. When x approaches 3 from the left, y is decreasing without bound. The left and the right side don't approach the same thing, so the limit does not exist. Finally, recall that when there's a hole in the graph, the limit as we approach the x-coordinate of that hole is simply the y-coordinate of that hole. If we don't have a convenient graph, remember that to find the y-coordinate, we simply plug in the x value into the simplified form of f of x. Remember that we had to cancel a factor in order for a hole to be in the graph. In example 6, just like when we graph rational functions, our first step is to simplify. Notice I have to repeat the limit notation. So do you. We canceled x minus 3. That's how we know that there's a hole at x equals 3. This is the number we're approaching, and so we need the y-coordinate by plugging in. Notice that when we plug in, suddenly we don't need the limit notation anymore. When we have a graph and we're finding a general limit, we're looking at what is y approaching as x approaches 1 from both sides. So x is approaching 1 from the left and from the right. The y-coordinate that we're approaching is -1. In other words, the y-coordinate of the hole itself. The same reasoning can apply even if there's not a hole. If x is approaching 0, y is approaching the point that's on the graph. Its coordinate -1.